Hello everyone, this is Astarag and today we'll be discussing on policy distillation. The motivation for on policy distillation comes from Thinking Machine's blog post on this topic. The main premise of using on policy distillation instead of reinforcement learning is the signal level that you or the feedback that you get from your trajectories. In reinforcement learning, as we discussed earlier, in algorithms like GRPO, uh, we assign one reward to the entire trajectory. So you are learning from an O of one signal. And but the need is to have denser signals or have token level feedback or have text based feedback. How can we use that for uh, in our post training pipeline? So, as we discussed, in reinforcement learning for language models, we frame it as a bandit problem where we accumulate the entire response token into a single action space. That way, we are losing token level feedback for each of those tokens generated in our response. To be more clear, we will go back to our example on transformers and see how RL for LLMs plays out. So in transformer, you have a beginning of sentence, and from we do a forward pass from all the transformer layers. We get back the logits. We do a log softmax, which the formulation is here, and from all our vocabulary, we pick the log probability of the token hello. Similarly, for the next token generation, we take the beginning of sentence, we take the hello, we pass it through all the transformer layers, we get the logits, log softmax, and then we gather the token world, the log probability of the world. So here you can see that the entire action space of beginning hello world can be converged into one uh, um, scalar, which is the sum of the log props. And RL for LMs like GRPO or DPO use this as a proxy for uh, compressing all the log props into the single action space. But this type of aggregation loses token level feedback, and we need to find a way to have token level feedback. For that, people have used techniques in Jeffrey Hinton papers on knowledge distillation. In knowledge distillation, you have a token, and we have a teacher model, which is generally a superior model or high parameter count. And we want to distill the capability from teacher model to the student model, which is low parameter count. We produce the log props from all uh, from the teacher and the student model, and the log props um, from the log props you can get back the probability by taking exponential. And if you compare these probabilities, you can find how these two distributions are different, and you try to match the student distribution onto the teacher distribution. We have something like KL divergence, which helps us to map two probabilities where we want to minimize or we want to see how different are these two distribution P and Q. To find that, we sample and then see the probability differences between these two distribution to get an estimate on how these two distributions are different from each other. So in distillation techniques, your aim is to minimize this difference in distribution between the teacher and the student. From building upon KL divergence, we have two flavors of KL divergence. Let's discuss the first one, which is called as forward KL divergence. In, in our notations, T stands for teacher, S stands for student. So the KL divergence between teacher and student here in my notations I have I'm writing these notations in log props, so you have to take a exponential of the log props to get um, the probabilities. And you can see these are the probabilities for the um, teacher logits, and these are the log props for teacher, and these are log props for student. So if you go back to the formula, we have this as teacher, and this as teacher, and this as student. So forward KL divergence, we would like to minimize the KL divergence as we discussed in distillation. Let's kind of play out hypothetical scenarios now. Suppose teacher assign for a token, teacher assigns low probability, and exponential is a monotonously increasing function. So uh, low probability leads to low value, and student assigns high value. So the KL divergence for this would be acceptable because your KL divergence hasn't shot up, because this term is outside and this term is after subtraction. So when it goes up, it's fine, like the KL divergence is low. But the other case where teacher assigns high probability for a token but the student assigns low probability, we get higher KL divergence in forward KL, and we want to discourage this. Hence the KL divergence would be high and the loss is inversely proportional to it, and we would like to bring down the loss, so or in turn bring down the KL divergence. So we would like the student to not miss out on high probability teacher tokens. So this means suppose this is your optimal policy and your teacher has some distribution like this in purple. Your student should um, cover distributions that teacher is saying high. So forward KL divergence is mode covering. Whatever teacher is saying as high probability, students should also assign to be high probability. So as we saw here, if teacher assigns high probability, students should also assign high probability, else this KL divergence is going to go up. So forward KL divergence is called as mode covering. And also you can see the student, if you are optimizing your student policy based on this teacher policy, it is trying to cover these two modes, and that behavior is expected in forward KL. But coming to reverse KL divergence, you can see it is flipped. Now student is on the front and teacher is here. And the formulation for it, if I go back to KL divergence, is Px, P on the forward comes here, Q on the backward comes in the denominator. So if I go back to reverse KL divergence, we have student and teacher. So student comes here, students is here, log props. We wanted probability, that's why we had to take exponents, and we have student and we have teacher log props difference. Now let's play out two scenarios. Suppose for a token, student assigns low probability and teacher assigns high probability. For this, the KL divergence is acceptable. The KL divergence is low. So this behavior is okay under reverse KL divergence. But suppose now student assigns high probability for a token and the teacher assigns low probability, this KL divergence is going to shoot up, and that is not acceptable. So we want to discourage tokens that have high probability under student but have low probability under the teacher. And this behavior is called as mode seeking, where the student has to avoid the low probability teacher regions and only go towards the mode of the teacher. So coming back to our visualization, we had the optimal policy and we have the teacher policy. We don't have this optimal policy, we're trying to approximate with the teacher policy. You can see, like in reverse KL divergence, it is converging towards one of the mode, because in reverse scale divergence it uh, it penalizes us if student picks up a low probability region. So this is a low probability region for the teacher, and the student is trying to avoid this part. So these are the two behavior when we are trying to do knowledge distillation or on policy distillation, where we have forward KL and reverse KL. So let's read through this. In forward KL, whatever teacher is saying as high probability, students should also assign high probability, and the behavior is mode covering. So as you saw in our visualization, the teacher had two modes, and the student also needs to have those two modes. So it has to cover those two modes. But in reverse scale, whatever the teacher is not saying as high probability or assigning low probability for a token, students should also not assign high probability for those. So students should actively avoid low probability teacher regions. As we saw here, these are the low probability, student is actively avoiding those low probabilities. In teacher student distillation, we in the papers like GKD, um, or the original on policy distillation paper, we were using reverse scale, and we did that because we wanted the student model to mimic the teacher model, and it should be more seeking there, as the teacher model is already good enough to solve our task, and we just want to mimic it with our student. Now, there are some of the more optimizations that we can do while doing on policy distillation. So if I go back to this slide here, as you can see here, it is considering all the tokens in our vocabulary. So it is a vocabulary size uh, list, and when we are comparing the difference between these two distribution for teacher and student, for each token in our vocabulary we have to compare the probability distribution. And this is expensive because vocab size is generally around the size of 250k, or the vocab size keeps on growing. So one optimization that people tend to do is, instead of taking the entire vocab size, you can take the top k high probability tokens and consider that to be your vocab dimension. And the top k can be 20, 30, 100, and it will be much less than 250k vocab dimension. So this is the first optimization that people tend to do with on policy distillation. The second optimization comes from DeepSeek V4 paper. I would really encourage you to check it out. And here, let's go through this slowly. So when we do a forward pass across a transformer, we have batch of sequences, and each sequence is of length t. So we have a batch of sequences, and each sequence is of length t, and we do a forward pass, and transformers layers are homogeneous, and they would have a embedding dimension called as d. So after doing the forward pass, you take batch of sequences, and we get back batch of sequences and embedding dimension, or the hidden dimension. So you get back this hidden dimension, and then we have something called as language modeling head, which converts this hidden dimension into vocab dimension, up projects into vocab dimension, where we get back the probabilities for each of those tokens. So and while decoding, we pick one of the tokens from our vocab size. Based on greedy decoding, you take the highest probability, or you can sample from any of the top k probabilities. So this vocab size is really, really long. As we discussed, it's around dimension of 250k, whereas the dimension of d is generally small. So when you materialize this, you convert into a vocab dimension, you are having such a big matrix. And DeepSeek had this problem where they had to transfer this batch size, sequence length, and vocab dimension across GPUs. And as this a very big matrix, so they decided instead of transferring this, what they would do is like they would take this batch size, sequence length, and D dimension, which you get from the forward layers, and you also take this language modeling head. You transfer these two things to another GPU. And if you see the memory consumption, if you have to transfer batch size, sequence length, and vocab dimension, you would have this much memory, and this V is really, really large. And but if you transfer the batch size, sequence length, and the hidden dimension, and as we mentioned, the hidden dimension is much smaller than the vocab dimension. And we also have, this is the language modeling head, which up projects from your hidden dimension to the vocab dimension. So the total memory would come around this, which is significantly smaller than this memory. So instead of materializing into a vocab dimension, they would store this intermediate and also transfer this language modeling head to save up memory. So these are the two optimizations, the top K and this DeepSeek optimization technique. Let's discuss another paper called as adaptive scaled distillation. In this paper, they were refuting two assumptions that we take when we are optimizing with reverse scale or forward scale. The first assumption is we are assuming it's a continuous distribution, but language modeling is discrete and it has a vocab dimension and it will be sampling from that. So it's not a continuous distribution. And the second one is, as we discussed in this visualization, here the teacher is bimodal, but my student distribution is converging to one of the modes. So the assumption that student distribution is unimodal, it's not valid, and these two assumptions lead to a formulation in the paper that we'll be discussing. So in forward scale divergence, as we discussed, we take the scale divergence where the teacher is first and then comes the student, and this is the formulation. And we wanted to encourage the behavior where the teacher assigns high probability and the student assigns low probability. We want the scale divergence in that case to be high, which is given from forward scale divergence. So in a sense, if you have this to be a teacher policy, so when we are optimizing by forward scale divergence, you are mainly targeting to the head of this distribution. Similarly, for reverse scale divergence, you have this formulation of student and then teacher. Here we have the student probability distribution first, and we have log props of student minus log props of teacher. So the scale divergence would be high when student assigns high probability for a token and teacher assigns low probability for that. The scale divergence would be high. So we are targeting for the low probability distribution in teacher. Hence, I have highlighted the part, if this is the teacher policy, in reverse scale divergence, we are trying to avoid these two areas for the student model to converge at. We need to avoid these two areas. So in adaptive scale, they propose, can we do this dynamically? This push and pull between forward scale, where the forward scale is focusing on the head or the high probability region, and reverse scale is focusing on the low probability of the teacher region. Can we do it dynamically. And in adaptive scale, they can come up with a formulation to make it adaptive. Here, they would have something like a mu parameter, which is 0.5, let's say, and they will assign the the tokens that have probability little more than 0.5 cumulatively. So suppose you have integer 0. Suppose your vocab size is 4 and you have these 4 probabilities which sum up to 1. So the head will be considered as T1 and T2 because these two sum lead to 0.65, which is more than 0.5, and these are part of your head and the rest are part of your tail. So in adaptive scale, you have these two distributions for teachers and student, and this is what we saw in the previous slide. So you assign the head and tail based on the cumulative sum. So this part is head and this part is tail with respect to teacher. So you see the difference in probabilities between your teacher and your student, and you make this column, which is the epsilon, which is given by p minus q, and you get the difference in probability assigned for head and tail here. So you can see like we got a difference of 0.05, 0.10, 0.06, which is, and 0.01. So we take the absolute value. So as this first two rows are head, so we just like sum the first two, and these are part of tail, so we just sum the next two. So the adaptive scale loss comes after that, where if the student is missing high probability teacher tokens, then the G head is high, and um, and if the student is assigning high probability to teacher's low probability, then G tail is high, which is from your reverse scale. So in adaptive scale, these ratios dynamically adjust based on where the probability mass is. If the probability mass for the student is um, is already in the same places where the teacher is giving high probability, so we don't need to consider forward scale. We don't need to optimize forward scale that much. We need to concentrate on the reverse scale because that concentrate on the low probability regions for teachers, which the student should avoid. And if the student is already avoiding the teacher's low probability region, so maybe we should consider on the student following forward scale prioritize uh, converging prioritize covering the modes of the teacher, which is given from the forward scale. So the metrics while doing on policy distillations are as follows. First metric is the average fraction of the tokens that appearing in both the students and teachers top k sets. So you take top k to be 100 and you see how many tokens overlap between the top 100 probabilities for teacher and the top 100 probabilities for the student. So this is given by the overlap ratio, and overlap token advantage just scales this ratio, scales this fraction of tokens by how much the teacher and student are giving weightage. So you can see that if you just consider the fraction of tokens that are overlapping, so even if you get really high average fraction of tokens that are appearing in both teacher and student, the teacher and student might give different probabilities to those tokens, and that is solved from this overlap token advantage, where we take the number of overlapping in, let's say, top 100 tokens from teacher and student. We weigh them by how much they are assigning probabilities for those common overlapping tokens. So, and the third metric is entropy. Entropy is given in this simple entropy formula, the Shannon entropy, where you take the probability and the log px. So this is generally done for exploration. Your entropy should not collapse, else your model will stop exploring. So these are the metrics that you need to track, and you can read through this paper to get more ideas on how they track these metrics and what kind of insights they got from tracking these metrics. All right. The next topic that we will be discussing today is called as self-distillation. In on-policy distillation that we discussed, we generally have a teacher model which is superior and it's performing well, and we want to distill that teacher model into a smaller student model for inference, saving cost on inference or deployment. But we generally don't have access to this teacher model, and we are bottlenecked by this teacher model. So, how can we have a teacher model with the same student model that we are training on? In self distillation, we have a concept of privileged information. So, we have a student model, and to build a teacher model, we will give this privileged information to the student model to verify the answer and give probability ratios. So the privileged information can be, let's say for coding, it can be the failed test cases or runtime error. And for math problem, it can be any solution or any reference solution that you can use to solve the current problem. So these are the papers that we'll be discussing today. Privileged information. So this is our reverse scale divergence that we discussed earlier, and we can see that privileged information is the differentiating factor between our student model and our teacher model. So if you have the same student and teacher model, how can you differentiate the teacher model? And the answer is giving it some privileged information and then optimizing the Gale divergence. So as we discussed, the privileged information can be failed test cases, reference solution, few short examples from similar task. And you can see that this teacher model has the prompt, the privileged information, followed by the output from the student model. And we need to assign weightage to, given this privileged information, how much weightage is our teacher model giving to this response. So let's say this code was bad and it led to some runtime error. So given this runtime error, the model can figure out which are the tokens that led to this runtime error. And the student model can learn from this privileged information in a proxy way by minimizing the Gale divergence with the probability assigned from the teacher model. So as we have different student and teacher model, we have few ways of syncing the weights for student and teacher model. One method is exponentially moving average, where we weight the student model by some 1 minus alpha, and from our previous time step we have some teacher model. So the new teacher model is a combination of the previous time step teacher model and the new student model. And also keep in mind that student model is what we are getting it trained on. So there are some other ways also. You can keep updating the teacher model so that it's not stale, is called as trust region optimization, where we keep a copy of the initial checkpoint and we try to minimize the KL divergence between the update and we keep it under a threshold. Or you can have the fixed teacher model and the teacher model never changes. We will discuss where fixed teacher makes sense. So um, as as we are discussing self-distillation, and the main differentiating factor is we don't have a teacher model, and for to make the student model behave like a teacher model, we show some textual feedback like test cases, reference solution, or runtime error to differentiate between teacher and the student model. But the self distillation has some problems. The uh, the good part of RL is it's scalable, and with verifiable rewards or rubrics, you can scale many generation. You can scale across lot of domains, and another good thing is in RL we have the reward, and that reward is helpful in knowing which trajectory is good or bad. But in self distillation and on policy distillation, we kind of discard that reward. So, and that might lead that the model might converge into bad rewards. So you can see here, uh, the student model has converged into teacher model for reward of 0. Ideally, we would like the student model to converge here at least, because it has some positive reward. And because of the student model doesn't know about the reward, it will converge poorly, and it will converge in one of the low reward section in teacher. So how can we avoid this? uh, we'll be discussing reward driven self policy distillation. So you have the student model, which takes the prompt, generates the response, and the teacher model is the same response with the same prompt with the privileged information. Now we have this uh, reward term, extra reward term, um, and um, and we want the behavior where the teacher model is approaching this optimal policy, because this optimal policy has high reward. As the teacher model is approaching this optimal policy, we want the student model to also approach the teacher model, and it should approach the teacher model where the reward is high, hence in this reward greater than 0 region. So let's see how we can do that. We will go back to this ML concept called as expectation maximization, and how it relates is you have this optimal policy that you want to approximate, but you don't have this policy. You only have teacher and student policy. So how can you have a loop where you are approaching with the teacher policy to this optimal policy, followed by the student policy is also approaching the teacher policy? So to do that, we will be doing expectation maximization, where we have uh, where we have two steps. First, we update the teacher, and to update the teacher, we have a reward region, and for regularization, we should not stray too much from the student distribution. Hence, you have a KL divergence here, which has the teacher with privileged information, and you can see this SG, which stands for stop gradient. When you are updating the teacher, you should not touch the student. So this is form of regularization, and you have this expectation on the reward. So the teacher model is now trying to approximate the optimal policy. So after you have updated the teacher model, now it makes sense to cover the mode of the teacher model. And here you, as you can see earlier, we had this bimodal distribution for the teacher, But as the teacher is now learning about the reward and approaching the optimal policy, it's going to converge to be unimodal. And when it is unimodal, it makes sense for our student model to mimic that distribution. So we want the student model to cover the mode of the teacher model. Hence, we'll do forward scale divergence here. So you can see here, uh, in we will optimize this scale divergence where we have that as we are doing forward scale, your teacher is here, and also remember we are updating the student, so teacher is not touched. So that's why you have a stop gradient here, and you are minimizing the scale divergence. Also, you are now weighting the reward by this importance sampling ratio. Um, and this comes from PPO, GRPO, where you have importance sampling ratio, where you have two distributions, and you want to weight them by the reward. So it is now a loop where you update the teacher and then you update the student, then you update the teacher, student, so that teacher approaches this optimal policy followed by student approaching the teacher. Now let's discuss how in recent post-training pipeline how people are using on policy distillation or self policy distillation. It is more like on policy distillation is being used in post-training pipeline. Self distillation is still a research area which is going on. Um, so in the MIMO V2 flash paper, what they did is they would take the SFT model data, they would train across domain like search agent, code agent, math, reasoning, safety. Across all this domain, they would have domain teachers. Now they have a collection of these domain teachers. Now what they will do is uh, all these are trained separately. They need to converge into one model. So they would take us the previously trained model, and they will try to distill all the teachers into this model and get the final checkpoint. So for each prompt, you will have completion from your student model, and that student model will be evaluated on different domain based teacher model, and you can get a with reverse scale you can optimize with this multi-teacher on policy distillation. So it's something like an analogy can be you let uh, different field experts come in to distill all their knowledge into one model. Similarly, in GLM5, they also had something like they take the base model, do SFT, do reasoning, agentic RL, general RL on different tasks like rubrics based RL. Now they would have this SFT model and they would distill them with logics with on policy distillation, and they got back the GLM5. Nemotron Cascade also had an interesting idea where they had this base model, they did SFT, then did instruction following RL, multi-domain RL, and then the idea of in Nemotron Cascade to use multi-teacher on policy distillation was while doing post-training, you go through many stages. You do a post-training on this data, then you post-train on that domain. So there is some catastrophic forgetting when you do SFT, and with RL it's less, and also with on policy registration it is less. So to regress or to get back the performance of previously trained checkpoint, they would have this multi-domain on policy distillation pipeline where they would take all the previous checkpoints and try to distill it into the current checkpoint so that there is no catastrophic forgetting from all the SFT or domain specific knowledge that the model gained. Also, the Nemotron Cascade 2 paper had an interesting variation in their multi-teacher on policy distillation, where they had this formulation where they would take the domain and the model that you're training now as alpha t here, the log price difference, and they would also weigh them based on this is the importance sampling ratio. If you have uh, heard about uh, training inference mismatch or importance sampling, how you can correct it. So this is just a simple importance sampling ratio to weight different domains and the student model, so that you can dynamically weigh how much each domain is affecting your distillation. So this brings us into all the post training pipeline. I would really encourage you to go through all these materials, and on policy distillation is emerging as a really important post training pipeline. And the main um, advantage is you can provide, as we discussed in self policy distillation, privileged information, which can be uh, test cases or reference solution, which are textual feedback. The issue with RL is you have to have a scalar feedback, one reward, but the feedback can be proper text, and on policy distillation or self policy distillation allows you to do this, to have textual feedback so that the model can learn. Thank you, and if you have any questions, I'm one comment away.